Hi everyone, in this video we will look at solving exponential and logarithmic equations and look at a bunch of examples. Now for exponential functions, they are what we call them a 1-1 function, meaning that if the results agree, then the input must have agreed as well. So for example, if I have to solve for 5 to the x equals 125, then I make the observation that 125 is 5 cubed, which gives me that x must have been 3. Similarly, if I know that 5 to the 2x equals 5 to the x plus 1, then the exponents must be the same. So 2x must be x plus 1, and then it becomes an equation that we know how to solve. Consider 3 to the x plus 2 equals 7. Find the exact solution expressed in terms of log. Now if you just look at this directly, we are unable to solve this like we did the previous two, because 7 is not a nice power of 3. However, that doesn't mean we cannot solve it, right? So what we do here is we're going to use our knowledge of logarithm to solve this. So we're going to say we take log base 3 on both sides. Now base 3, because I want to get rid of this exponent. And the only way to get rid of an exponent which has a base of 3 is to use a log function which has a base of 3. So this becomes x plus 2 equals log base 3 of 7, or log base 3 of 7 minus 2. Solve 8 e to the 2x equals 20. So we're going to first get rid of all these numbers in front and make this nice. Making this nice, this becomes 2.5. Now, same story as before. Because I want to get rid of the exponent, I'm going to take log base e, which now we can write as ln. And the whole point of you taking the log is that it cancels out the exponentials. So you get 2x is log of 2.5, or x is 1/2 of log of 2.5. Let's look at a third one. E to the 2x minus e to the x minus 6. Okay, now this is different. There's a 2x and then there is a x and all of these involved. However, we're going to use an old trick here, which is the quadratic-like equations. How is this quadratic-like? It's quadratic-like because e to the 2x is basically e to the x whole squared. And now, if I make this substitution u equals e to the x, this is nothing but u squared minus u equals 6, which factors into u minus 2, or u plus 2 and u minus 3, which gives me u is negative 2 or u is 3. Now, what is u in terms of x? In terms of x, u is e to the x. This is not possible, right? If you recall the graph of the exponential function, what does the graph of the exponential function look like? Like that. It's never negative, right? It can be as close to 0 as you want, not 0, but also never negative. This may give me a solution, and indeed it will, because it is positive. So I take log natural one. So this becomes natural log of e to the x is 3, giving me log of 3, ln of 3. So, which means that we can also combine this with our previous tool or with our previous things that we've learned, like quadratic-like equations or quadratic equations or factoring, as is the case in the next one. Now here, I can factor out an x and an e to the x, and I'm left with 3 plus x equals 0. That gives me x times e to the x is 0, or 3 plus x is 0, the latter of which gives me x is negative 3. Now here, this is never. E to the x can be very, 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 very small. You can make it 0.0000, so on and so forth. But it can never actually be 0, which means that the only possible, this is only if x is 0. So we either have x is 0 or we have x is negative 3. Okay, nothing other than those two. Next one says solve log of x squared plus 1 equals log of x minus 2 plus log of x plus 3. So now we are moving on to equations involving logarithms. So we did half of this. We did like the tools in order to solve this problem. For example, because these are two different logs, I can combine them. When I combine them, they become a product. So it's x minus 2, x plus 3 equals log of x squared plus 1. This further, if I FOIL this out, this becomes x squared plus x minus 6, which then becomes log of x squared plus 1. From here, I get the equation x squared plus 1 equals x squared plus x minus 6, which at this point now is just not even a quadratic anymore, because the x squared cancels and this just is x is negative 7. Now here, however, we have to be a little careful. Why is that? The reason is when you verify, right? When you verify your left-hand side, you are going to get log of negative 9 plus log of negative 4, which is not defined. Remember, the domain of the log function is actually the range of the exponential. So the domain of the log function, if you recall the graph even, is all positive, right? And that's how we found that domain in that example for log of 4 minus x squared. So this means this is not defined, so there is actually no solution. Because the only things that can be solution, or the only thing that can be a solution, is negative, and negative numbers cannot be put as input for log function. So the whole thing doesn't have any solution at all. So again, you have to be careful about the verification part. Let's go one more example. Now in this case, just as imagine you were solving for x, you would try to isolate it. Except in this case, you're not solving just for x, but for log of x. So I would subtract 4 to give me 3 log 2x is 12. Then I would divide by 3 to give log of 2x is 4. Right? So that log, this just means this is log base 10. Right? If it's log base 10, then I take the exponent and this becomes 10 to the power 4. So x becomes 10,000 over 2, which is 5,000. And you don't have to verify completely, you just have to check that you're not inputting something that is going to break the function or cause some trouble. So here you can see that because x is a positive number, when you plug it in there, it's still going to remain positive. One more, it says x squared equals 2 log x plus 2. Okay, now this is kind of strange because you have an x squared, you have an x, but then all of these is inside a log function. Okay, so what I'll do is, let's use the property of log to say this is x squared equals log of x plus 2 squared. Now, I want to get rid of the log, so this is going to become an exponential. E to the x squared is x plus 2 squared. Okay, so sorry. So right here, there's a typo. This should be ln of x squared here, or this cannot be solved. Okay, so this will give you x squared equals x plus 2 squared. And so that gives you x squared. So you subtract and you get x plus 2 squared minus x squared is 0, which gives you, again, difference of squares. So x plus 2 minus x and x plus 2 plus x equals 0. This gives you nothing. This gives you x is negative 1. Now in this case, negative 1 is allowed. It makes sense because even when x is negative 1, x plus 2 is positive. So negative 1 is a solution. Okay. So even if you do not completely verify, you have to check that the answer that you're reporting as your solution, which you got from all the work that you did, is actually something that can be put into the equation. And the reason you have to be careful with log function is because unlike exponential, log has a restrictive domain. Right? You cannot put negative things into a log function. It's not going to give you any output. So you have to make sure that whatever you're trying to put into the log function is positive. Okay, so this says a sum of 5,000 is invested at 5% per year. Find the time required to double the money if compounded semi-annually or continuously. So I'm going to do the continuously one, and you can do the semi-annually one as a bonus if you would like, and email me your result. So for continuous, we have amount is P times ERT. So we have all the amount here. P is 5,000. I want my amount to be doubled. So double of 5,000 is 10,000. Interest rate is 5% per annum times T. So basically solving for T, I divide by 5,000. 2 equals e to the 0.05 T. To solve for T, as before, I take logs. So log 2 becomes 0.05 T, or T is log 2 over 0.05. You can leave that answer in that form. You do not have to use the calculator to further simplify it. Unless the question explicitly says find to 2 places of decimal or something, you don't have to use a calculator or do anything. So when you're solving log equations, you may have to use exponentials to get rid of them in the last step. When you're solving exponential, you may have to take logs to complete the last step. That's pretty much all of it. So those were just some applications and some examples of solving for exponential and logarithmic equations. That's it. That's the end of this topic. Thank you.